team. Now team. Just a second.
Yes, visible.
No, not visible. I'm about to change the slides. So I think it's not happening. Oh, can I see here? No. Please, can someone confirm, like, if I want to change the slides, like, now is it like
Yes, sir.
which slides? MOSFET switch only, right?
Yes, sir.
Okay. Thank you. Okay, team. Actually, we are at the module 2 team, the MOSFET switch. Like in previous session, we have discussed about some S model. Like here you can see like what is the basic switch operation and how it operates, what about the VI characteristics, and then we introduced MOSFET. Of course, here the MOSFET based switch, whatever you are seeing, it is a bidirectional switch because MOSFET is a symmetrical device where you can exchange the source as drain, drain as source. So it is like a symmetrical switch, and you can see the VI characteristics as well. And here, just like a diode, it is like ideal model and practical ideal diode and practical diode. Similarly, in the same way, even in MOSFET as well, we have two types of like approximations. You can say like it's a S model and SR model. Here where SR refers switch like a switch and resistance. Like if someone wants to speak. Hello?
Hello? Just
Is
continue.
it?
Just continue.
Yeah, okay. Okay. Yes, team. So like switch and resistor model, in previous class we have discussed about switch model, like what about inverter, NAND gate, NOR gate, and we have practiced some exercises also. Now in this like session, we are going to discuss about SR model and even some power aspects as well. So in today's session, we want to close regarding the MOSFET, and in the upcoming sessions, we want to discuss about the timing, like time, what is timing arc and all. Okay. Now let's continue. Here, these and all we have discussed already. Yeah. Now, team, let's start for today's class session. The SR model. Team, we know whenever the MOSFET is in off state, it acts like an open circuit, and that is possible. You can see here, it's a VGS less than VT. Whenever the input voltage VGS is less than threshold voltage, it acts like an open circuit because the device is off. However, whenever the threshold voltage, I mean, the gate to source voltage or input voltage is more than VT, the device enters into on state. And of course, whether the device is in a linear region or saturation region, it depends upon the VDS value. Of course, that you get from basic electronics. But here our point is, whenever the VGS voltage is more than VT, the device enters into on state. Yes, in S model, there was no resistance. We assume it to be ideal resistance is 0. Whereas team, here in this case in SR model, whenever the device is on, it has some finite resistance or on. Yes. So here you can see one observation from these two figures, whether the device is on, whether the device is off. It doesn't matter. IG is equal to 0 only. You can see here. Because in a MOSFET, from the construction point of view, the MOSFET has some SiO2 layer, which can act as an insulator. So here, whether the device is on or off doesn't matter. Still, the gate current is 0 only. This observation you must remember. Remember, guys. Now, with this SR model, the basic behavior, let's enter into like inverter. And here we are seeing the inverter, NAND gate, NOR gate. It is not like what we have discussed or what you people come across in your academics, like NAND gate or NOR gate and all. Here we want to see the NAND gate or NOR gate with respect to static discipline. That is the main agenda of this class, PD concepts. Because whenever you go to like project, and whenever you are like when you are about to start the project, then you may get a doubt. Are these many standard cells are there? 1 million standard cells are there. What about noise? The noise may affect the cells. No, definitely it will affect. No doubt about that. Then how come it can survive? And all these doubts you may get it. So if you learn these PD basics in an efficient way, then during the project or during the synthesis part or PNR part, you don't get any doubts. That is only the intention. Like Rajat came forward and he wants to conduct these classes before PD. Okay, now let's come to the point. Here, see the VI Cat 6 of SR model. Team here, whenever VGC is greater than VT, yes, there is a current. But even you can see here from Ohm's law, in this circuit, if you want to find out the current, what about the voltage VDS and the resistance R on? The same thing you can see here, VDS by R on. Whenever VGS is less than VT, yes, there is no current at all. So the current, the current is zero. Now, team here, you see the device on resistance R on. We want to see that R on resistance is directly proportional to the sheet resistance Rn, where it is resistivity by thickness. In VLSI industry, we call it as a sheet resistance, and usually the thickness is constant, and that what we call the resistivity is also constant. When it comes to the PD, I told you in the beginning, we deal with the standard cells onwards. The design people, memory layout people, or analog layout people construct the standard cells, various standard cells. But that is not our domain. Our domain is getting the standard cells for our design, and how you place, how you meet the timing, and other aspects. That's it. So we deal with standard cells onwards. So in our aspect, here the thickness or conductivity or whatever, resistivity, whatever, are constants to us. Now, let me speak about the device on resistance R on is Rn by Rn into L by W, where that is the length of the conducting channel. W is the conducting width of the conducting channel. Most of the people remember length in a correct way only. That's what, from source to the drain. Guys, I told you already, if you are working at VLSI industry, especially at back end, people may ask you, Arey, on which technology you are working? 70 like 7 nanometer, 28 nanometer, 14 nanometer, 1 nanometer, or 130 nanometer. So you have to tell, yes, what is the technology? That is simply the distance between the source and the drain. You can see here. This is the source and this is the drain. Hope you know, or else I'll take some other pointers. Just a second. Yeah, see, here the source and here the drain. This gap is the channel length. And people think channel width is in vertical way. No, not at all. The width is Z direction, means in this way. You can see here the width, and you can see here the length. Here team, here why I am taking this much in detail. This is a very, very small topic. Yes, I agree. But is it necessary to discuss? Yes, it's very much needed, because you must know regarding the cell resistance, R on resistance, that is directly proportional to the length of the channel, length, and inversely proportional to the width. Remember team. Okay. So here, once the technology is fixed, the length is also fixed. So You don't have any rights to change the length of the channel. Then you have only one parameter left over, guys. That's none other than width. So if you want to change the resistance of the cell, then you have only one parameter to change, control, that is W. Okay, remember guys, that's what. Here from this slide, one thing you need to note down in your notes, that is Ron is directly proportional to L by W, especially Ron directly proportional to 1 by W. If not guys, if you're not mentioned, please note it down in your notes. You must have a separate notes for this particular course PD concepts. Okay, now let's move on. Yes guys, see, let's take the inverter. Guys, case 1, our voltage or VGS is greater than VT, because you can see here Vn is high. Then definitely this MOSFET becomes on. We are discussing NMOS inverter only. Later we will discuss CMOS inverter as well. But coming to here, this NMOS inverter is uh, this NMOS device is on. So it has some resistance R on. Then what is the output voltage? Previously we had V out as 0. You can see here guys. See, just a second. Yeah, see here. See, whenever this V out, whenever the device is on high, then you will get output as VOL. So that here this acts like a short circuit. You get VOL as 0. But whereas now in SR model, yeah, in SR model, by using some networks theory related formula, like if you ask me, I can tell you the formula as well, voltage division principle. So across resistance by total resistance into total voltage. That's what. Across resistance R on by total resistance R on plus RL into total supply voltage Vs. Now this is the formula for V out. Okay. Now you see here, uh, here the Vn is low guys. Sorry guys, here there is a mistake. Here V out is, whenever Vn is low, here V out will be Vs, because the current flowing through the rail to rail means Vs to the ground is 0. As there is no current through the rail to rail, the drop across the RL is 0. As there is no drop across the resistor, then this Vs will appear across V out only. Okay guys, so here it is not 0, it is Vs only. So I can say here RL, I mean Vn is high, V out is, like we will come to know what are the values and all. Here whenever you give the high input voltage, this Ron has some specific resistance, not very high. So you get some nominal minimum value only. And in this case, case 2, where Vn is low, V out will be logic, logic 1, which represents Vs. Hence you can say it's an inverter only. Now let's see the next one. Yeah, you see guys here that NMOS, yeah, just a second, yeah. Now you can see guys, inverter transfer characteristics, SR model, VOH. That means the output logic 1. Then it is a Vs only, because in the previous figure we considered this. Here V out is Vs only. Whenever the input is low, you get output as logic high, which represents Vs. Similarly, if it is VOL, that comes under like Vs into R on by R on plus RL. It has some considerable value, that is VOL. That's output side. Maximum voltage, minimum voltage. Now team, here I want to know about VIL, VIH. VIL, VIH are the voltages from the input perspective. Let's assume, just a second. Yeah, here guys, there is one uh, driver element. and there is one more driven element. Yeah. Now guys, see, for example, if this is my input, like logic, let's assume it is let's assume logic 0. In between the noise might be interfering. Then this whatever voltage, it may get enhanced. Let's assume that is actually this device threshold voltage is 1 volt. Let's assume. Now here, uh, because of the noise 1 volt, here this second driven element is receiving 1 volt signal. Then what this driver element think? What is this driven element think? Okay, I received logic 1. I have to send logic 1, like that it will think. But actually the driver element sent logic 0, right? In the same way, what how you should go means, here for VIH, which represents logic 1, it could be any value, but it must be, just a second, control. Yeah, guys, this VIH, what it represents logic 1, right? So that value VIH must be any value greater than or equals to VT, because then only the device becomes on, isn't it? Yes. So what is the point means, as VIH represents the minimum value required to represent logic 1, to represent this particular driven element to enter into on state, it requires V more than VT. Hence here we said it is VT plus, means uh, somewhat a very minor value more than VT. Suppose VT is 1 volt, then VT plus will be like 1.001. Yes. Similarly, VIL represents logic 0. It is the max value to represent logic 0. If it is logic 0, the device must not become on because it's a logic 0, right? Hence, the VIL value must be less than or equals to VT. Because if it is equals to VT or more than VT, it can recognize as a logic 1. But VIL is the max voltage for logic 0. Hence, guys, VIL from the standard, like what we call the static discipline, you can consider it as VIL VT minus. That means a very small value less than 1 volt. Means that could be VT minus is like 0.999 or 9, like this. Very small value which is less than 1. Okay, in this way, guys, since previously, guys, I want to conclude this SR model inverter with S model inverter. There you can see, like in your notes, VOH VS here and there, VIL here VT minus, there also VT minus, here VT plus, there also VT plus, but only one change is there here, that is VOL. Here VOL is RR by RN plus RL into VS. There it is 0 only, and you can see, like I can show you here. See here, SD analysis using S model. Everything is same only except VOL. Here the VOL is different. That is the reason you can see the VI characteristics here. it is at the horizontal line, but whereas here in SR model, it has some particular value. See here. This is the difference, team. Okay. Now let's move on to one numerical. See guys, here calculate the static discipline for the following NMOS inverter. Assume VSC is 5 volts, VT is 1 volt, R on 1 kilo ohm, RL is 14 kilo ohm. Now guys, can someone calculate VOH, or can someone tell what is VOH, team? Team, I want some interaction from you people. Okay, so that then only it gives energy to me, it gives motivation to me. Can someone tell what is VOH?
5 volts.
Yeah, very good. VOH is equal to VS only. It's 5 volts only. What's your name, team?
Honey.
Funny. Okay.
Honey,
Good,
honey.
funny. Honey. Okay. Yeah, honey. Good.
Yeah.
I thought honey means it could not be honey, but anyway, it could be anything else. Well, fine. Good. And here VT is 1 volt. Then what could be the VIH? VIH is the minimum voltage to recognize as a logic 1. What could be the VIH?
1 volts. Slightly
Not
greater
1
than 1
volt.
volt.
Yeah, 1 plus. Similarly, VIL, which represents logic 0, is, yeah, honey.
Slightly less than 1 volt.
Good. VT minus. Now, guys, it's time to discuss about VOL. VOL is the voltage at logic 0, the minimum voltage, like logic 0. Now, according to the voltage division principle, it is R on by R on plus RL into Vs. That's none other than here. Just a second. Yeah. See here, guys. The solution. VOH is 5 volts. VIL is okay. I think this theme is not supporting, guys. Actually, that is a VT minus that VIL, and VIH is VT plus, and VOL as well. It is R on by R on plus RL into Vs. That is 0.33 volts. Yes, guys. Now, guys, I want to revise one more time for a better noise, like for a better ability. Is a cell must have high noise margin. To get high noise margin, we have VOL, and the VOL must be as small as possible. From the noise margin equation, the noise margin low is NML is VIL minus VOL. For the better noise margin, VIH must be VIL must be maximum, VOL must be minimum. But here this VOL is 0.33, but in S model it was 0 volts only. Now 0.33 is there. Be careful. The noise margin is less. Okay. Now let's go to the next numerical. Problem 2. You read this question, guys. Does our NMOS inverter, whose static discipline is VOH, VIL, VIH, VOL, satisfy this static discipline used by the DISCO systems? See, the system is very important. With respect to the system only, we need to work on it. Assume that system's static discipline is VOH 4 volts, VIL 1.5 volts, VIH 3.5 volts, VOL 0.2 volts. Now, guys, let me recap. The noise margin is VOH minus VIH. Similarly, noise margin low, VIL minus VOL. Yeah. For better noise margin, VOH must be maximum, VIH must be minimum, NML is for better high noise margin. VIL must be maximum. VOL must be minimum. You see, this is our reference, 4 volts. Whatever might be the value, the VOH value of a device must be more than system's VOH value, which is 4 volts. Here we are getting 5 volts. Wow, very good. It's more than enough. Satisfied. VIL is 1.5 volts. We want VIL to be maximum, I mean more than the device, I mean system value. Here the VIL value is 2.5 volts. Wow, here also satisfied. Now VIH is 3.5 volts. VIH must be smaller than system's value. Here the VIH is 3.5, here it is 3.25. Yes, it is also satisfied, but whereas 0.33 is VOL. But here what is VOL of systems? 0.2 volts. So guys, in this case, we don't use these NMOS cells or devices as it is failed to satisfy VOL, because VOL we are expecting less than 0.2, but here this device has 0.33 more than the system's value. Hence, it is failed to satisfy the static discipline. Hence, we don't use it. Now we want to troubleshoot. Now the whatever that device, the vendor is in a dilemma. Array, now this disco systems people are not using our cells. Okay, Tenicast, I want to let you know, I want to use this in some other devices. Now how can I overcome or how can I fix this VOL issue? That is only the point. So here, how can we fix the VOL? Let me recap. See guys, here you can see system designer, vendor. VOH is 4 volts and there it is 5 volts. All are satisfied except VOL. So we don't use given vendor cells as VOL is not satisfied. So what's the solution? The solution is simply you take that value. What is VOH? Actually, VOL is R on by R on plus RL into VS. Whatever the value you take, and that must be that VOH must be greater value na, and the whatever the value you are going to get in that circuit, that must be smaller. That's what here I have mentioned here, that VOL value of a system must be greater than the device VOL, that is R on by R on plus RL. We have 3 choices here. You can change the VS, you can get this satisfied equation, or by changing the RL, you can change the, I mean, you can get the value less than 0.2, or else at the end, we have R on resistance also. That's what we have written here. By reducing the VS or increasing the RL or reducing the RN, you can achieve this condition. But you know, guys, whenever you go for reducing VS, it will affect the noise margin actually, because the total boundary you are reducing, then it may not be a correct solution to us. Then don't consider them. Similarly, RL. If you increase the RL, then also you can fix this problem. But we don't do it because if it is a high resistance, there will be high power dissipation. Normally in VLSI, we don't consider high resistance devices, I mean load resistances and all. Hence, that's also not fine. Then we have only one option, guys. That's none other than R on. That's what here you can see here. RL you can take 24. By choosing RL 24, you can do that, but we don't do it because in VLSI that is very hard to get those kind of values. Hence, the possible solution is R on. By getting the changing the value of RL, I mean width and W values, you can get that value to less than that 0.2 volts. So here you can see by taking the VS 5 volts, RL 14 kilo ohm, here this R on is like if R on is 0.58 kilo ohm, less than that, then you will get it. So here, what's our intention is, guys, here mathematics, how you got 0.5, it doesn't matter. I want to tell you only one thing. By changing the width and the length ratio, W by L ratio, you can change R on. By changing the R on, you can fix VOL. By fixing the VOL, the systems, the disco systems or some XYZ systems may use your standard cells or your cells, whatever. So here, the only hope where the static discipline is failed, the only hope is none other than width by length ratio. Even you can see here one more numerical that you can take it as a homework. Okay. But here, what's our intention is, if you want to fix the static discipline where it is failed, by changing the W by L ratio, you can fix that particular issue. That's what the point, team. That's it. No more mathematics and all. Here, forget about the mathematics, what you have practiced at your undergraduate levels, like in BE or BTech. It is totally physical design. That's more than you think. There is a lot to learn, there is a lot to analyze that you will do from synthesis. But here, what and all, here we are discussing the PD concepts and all. That gives you a glimpse, that gives you one what we call one glance to enter into PD. That's it. Okay. Now let's enter into like the very two important properties, team, regarding the MOSFET. What is the first point? Ig is 0 irrespective of the on off condition of MOSFET that we discussed already. Second one, no impact of ID and VDS of a driver element over driven element. Guys, that's what I want to tell you. Yeah, just a second. Yeah, you see here, there is one MOSFET. This is a driven element. And this is connected here to one more MOSFET. The second device, right hand side device, is driven element. Let's assume. Now guys, here, just a second, I want some other colors. Yeah, guys, here there is a current, ID or whatever. This is the ID. And of course, here there is a voltage as well, VDS. This ID VDS of the driver cell is not going to affect on the driven cell, because here SiO2 layer is there. Because of this SiO2 layer, what might be the ID or VDS, it is not going to affect on the driver element, I mean driven element. So that's what here, no impact of ID VDS of a driver on driven element over driven element. So these are the excellent properties
Yes,
of the
to
MOSFET.
rejoin the same link. To rejoin the same link.
What?
Just rejoin the same link if the meeting got ended.
Okay, okay, okay. Can I stop now? Yes. So guys, here, hope you are seeing my screen. Okay. So guys, here, first of all, irrespective of the device status, Ig is 0. And one more thing, the driver element ID and VDS are not going to affect the driven element status. Hence, you can connect n number of devices at the output of the driver element. Hence, remember guys, the fan out could be maximum. The fan out of like this particular MOSFET you are considering is maximum. Remember guys. Now, let's see the two input NAND gate. You can see here guys, VOH is Vs 5 volts, VIL VT minus VIH VT plus only. The only one thing that is different is VOL, which is Vs into 2R by R plus RL, because in NMOS inverter NAND gate, the NMOS cells are connected in series. So that here 2R by 2R plus RL plus RL into Vs. So here VOL, guys, somewhat maximum value, because two resistors are connected in series, no. So you will get VOL somewhat maximum value. But to be frank, for better noise margin, VOL must be minimum. But because of these two resistors, VOL is even more high value than inverter. Similarly, let's see for NOR gate what it could be. As the NMOS transistors are in parallel, whenever you want to calculate VOL, the two resistors are in parallel. Hence, the equivalent resistance is R into R by R plus R, which is R by 2. You get R by 2 plus R by 2 plus RL into Vs. That means compare with NAND gate. Here in NOR gate, the VOL value is minimum. So guys, the very important interview question on VLSI fundamentals and PD concepts, none other than in which gate and in which universal gate the noise margin is high. Means with respect to the noise margin, which device is better? None other than the NOR gate only, because the VOL is less, but in NAND gate the VOL is somewhat high. That's the reason if someone asks you in your interview which NAND, like whether NAND gate or NOR gate, which gate is better, which gate has a better noise margin, none other than NOR gate only. Now guys, see that's what the conclusion. A NOR gate has high noise margin over NAND gate due to less VOL. Hence, what are the maximum number of input that you can give to the NAND gate? Means only two. See, if it is a gate, means it must have minimum two inputs. That's why we are saying the minimum value 2. That's it. Whereas coming to the NOR gate, the maximum number of inputs could be infinite. So that if it is infinite, right, R on by infinity, you will get it. Means you'll get 0. So that VOL becomes 0. It is moved towards ideal. Hence, the maximum number of preferable inputs of a NOR gate, is infinity. But whereas it comes to the NAND, it is 2 only. These are the conclusions, guys, which we are concluding after this MOSFET switch. Okay. Now, next go to load capacitance. Guys, usually in our BTech academics, we think with respect to the load resistance. The device has some resistance, which is a load resistance RL. We are mentioning that. But whereas now, this particular inverter has some capacitance CL. From where you got this CL? We want to know. It is simply, you can see here, this is a driver cell who is driving these cells. Hence, it is a driver cell. Usually in our buses or in any cars and all, driver will be in the front position, front place. But in our VLSI, it looks here at the, back side. So he is a driving force to all these driven cells. Okay. Now let's see. See, this driver cell has some driver. This you can see here. Uh, yeah, he has some drain to source capacitance, CDS. Similarly, all these driven cells have their gate to source capacitance, CGS as well. And guys, see this net. This net has some resistance, right? Like the virtual resistances and capacitances. If you take that net capacitance, that wire capacitance, you can see here. So that is the CL. The load capacitance is in terms of, it is the addition of wire capacitance of net, drain source capacitance of driven cell, and gates like that input capacitance of these cells, guys. These are driven cells. Okay, this is what the CL, the load capacitance. Now let's see, guys. We want to know about power. Okay. Now let's see some basic mathematical, some fundamentals from basic electronics. That is the power consumption. Whenever you take one RC circuit where you can see the right hand side, and whenever you are supplying the power supply, VDD, suddenly the capacitor takes some time to get charged. The steady state value, how much time it requires, is 5 tau. Usually, the steady state, it may reach the steady state after 5 times the time constant. It's a 5 tau. During that time, if you ask me the power, that instantaneous power is P is equals to V into I, VDD into I of t. Whereas the instantaneous current, that is simply the voltage VDD, and here whatever the capacitor voltage VC of t. That's what here, VDD minus VC of t by resistance R. And what about the instantaneous voltage, I mean voltage through the capacitor here? That is like the basic equation, VDD into 1 minus e power minus t by t. Okay. Now this is the instantaneous voltage through the capacitor. Now with these fundamentals, let's go to like the power equation. What is the power equation? VDD into I of t. You can see here. Now we are substituting this I of t in this equation. See, VDD into I of t, where it's that's if the initial voltages are there, then it is a VDD minus VDD into 1 minus e power t by t by R. And when you simplify, you get VDD square into e power minus t by t in divided by like that by R, guys. So you know what is the formula for energy? That is power into time. Whenever you take the power, this numerical, I mean this formula, into the time and integrate from 0 to infinity, we will get the energy formula, guys. That is CVDD square. Means whenever it is on, the capacitor is charging, and how much energy it is consuming means it is like from the power supply means it is CVDD square. That's what here, CVDD square. Whereas here you can see the total power drawn from the power supply is CVDD square. And we know the energy stored in a capacitor is half CV square. Then what about the remaining half? See, the total supply coming from the power supply is CVDD square. Okay, the energy stored in a capacitor is half CVDD square. And the remaining half CVDD square energy is dissipated as a heat at the resistor only. Let me speak about the inverter. Okay. And whenever, for example, this is about the charging intervals. But what about the discharging? Whenever the capacitor is discharging, guys, that voltage equation will be obviously, you know, see, you can see here, the capacitor is discharging like this. So it is exponential decay function. Hence, it is VDD into e power minus t by tau, where it is tau, guys. So this is the basic equation. Now, let me speak about NMOS inverter, guys. This is the NMOS inverter equation. I mean, the circuit. Now, let's see here. Whenever Vn is 0, means this Vn is in red color, guys. This is Vn. Whenever input is 0, output will be logic 1. Because even though the device is off, there is a current flow through the capacitor in this way. So the capacitor is charging now. Whenever the capacitor is charging, guys, that too, as the output becomes on, it takes some time. I told you it takes some phi tau time constant to reach logic 1 in this way, guys. So now the output is getting logic 1 from logic 0. So here the capacitor is charging and the energy stored here simply like CL VDD square, and guys E2, and means here guys, once it is completely charged to a maximum value, for example 99.99, it is charged to maximum extent because it requires phi tau. Phi tau time constant is enough to reach the maximum value 99.99%. Then there is no any required energy. So it is, you can say it's almost 0. Okay, guys, this what happens in the power dissipation of like in NMOS inverter whenever Vin is 0. Similarly, whenever Vin is logic 1, see here there is a drastic decrease in the supply, decrease in the output voltage, and then here there is a stable logic 0 as well. That you can see here, guys, where Vn is 1, MOSFET is on. Now the capacitor is discharging in this way. As the capacitor is discharging, guys, you can see in the figure this delta L or this delta, whatever the value, is very, very less. As the value is very, very less, whatever might be could be negligible because the value is very less. Hence, E3 is the dynamic value only, but it is a very, very less, guys, 0. But whereas V4, where the output is logic 0, here there is a like a dissipation that is called VDD square into T by 2RL. This one, guys. So here what I want to conclude is the average power dissipation of an NMOS inverter means like the that total energy by time is the average power, means E1 plus E3 plus E2 plus E3 plus E4. Okay, so here that is E1 CL VDD square, E3 and E2 zeros, E4 VDD square into T by 2RL. When you divide the power dissipation into static and dynamic, where the dynamic contains the frequency term, where the static doesn't contain any time period. So there you see FCL VDD square is the dynamic power and static power VDD square by 2RL. Guys, we know the static power is very much greater than the dynamic power because that VDD square by 2RL value definitely greater than by VDD square by CL into F. You can see, guys, here it takes the time constant phi tau phi RLCL, and this is 2 RLCL. Definitely phi RLCL is greater than 2 RLCL, which is more than 1, which is a 2.5. So here I can say P static by P dynamic is greater than 1. That means P static is greater than P dynamic. Okay, so we conclude P static is more than P dynamic. Yes, static power is much greater than the dynamic power. We want to reduce the static power at any cost. So guys, till now we have discussed about NMOS. Yes, but here there is a very serious problem of the static power. How you can overcome the static power? The solution is simply changing the logic like a family. which is a from NMOS to CMOS. Whenever you go to the CMOS, there you don't get any static power. Let us see here. See here. You can see even some possibilities by reducing the VDD or by increasing the RL. We don't take these two options as it is affecting some other parameters. Hence, we go for the changing the technology to CMOS. Yeah, here you can see the buffer as well. Just let me tell you. Yeah, see this one, guys. So these are the disadvantages of PMOS and NMOS. Hence, you are going for CMOS. Okay. Now let me come here. Guys, what the observations we made in NMOS inverter. There is a huge static power dissipation. Moreover, the charging time constant is RLCL. You can see here. Yeah, you see here, guys. Here you can see RLCL. Here, the charging time constant is RLCL, where the RL value is very high. It is a passive load. Usually it contains high value only. Hence the charging time constant is more. But whereas during discharge period, it is the discharging time constant is R on CL, where the R on value comparatively less. I'm not saying it is very less, but compare with RL, it is very less. Hence, I can say, guys, the charging time constant is very much greater than discharging time constant. Okay. Now, let's enter into the observations again. The charging time constant is more, static power dissipation is more, and guys here there is no possibility to reduce the static power without affecting some other parameters. So we don't take this one. And even uh, if I increase the operating frequency, the dynamic power is going to be increasing. Yes. So these are the observations that we made at NMOS inverter. So we want change. We want something new, which can overcome, which can fix all these disadvantages, all these issues. Okay. Let me wait for a hold. Let me hold for a second. Before going to discuss about CMOS, we see NMOS buffer. What is NMOS buffer? Is this NMOS buffer? Because people say if the if input is 0, this acts like a open circuit so that the current flowing through this is 0. So voltage drop is 0. Okay. We have given input 0, output as 0. Buffer. No. Let's give input as 1. This NMOS becomes on so that current flow through this load resistor. Hence, there is a drop across this resistor, which is a VDD only. So it's a logic 1. We applied 1. We got 1. So can I take this circuit as NMOS buffer? No. Why? What is the solution? See, this emoji is not happy. He's saying he's showing the finger to downwards. Means he's not happy. Why? Because guys, whenever you take the circuit and you apply whatever that VDS analysis, whenever you give 5 volts here, here you get 4 volts. Because guys, if it is 4 volts, then only it satisfies that saturation region equation. Okay. So whenever, like, what's our point is, as the number of stages are more, the output value reduces. After few stages, this 5 volts logic 1 may reach logic 0. This should not happen. That is the reason we are not considering the previous circuit, which is a NMOS buffer, this one is not at all NMOS buffer. Then what is the solution? Simply two inverters. You take this inverter, you connect to one more inverter, then connection of two inverters, simply one buffer only. Okay, this is buffer. Okay, guys, sorry for my handwriting. Yeah, this is the buffer, guys. Now it's time to discuss about uh, disadvantages of PMOS. Okay, yes, there is a huge power dissipation. Noise margin is very less because VOL is maximum. To get high noise margin, VOL must be minimum, but here it is high. And even the charging time constant, where the output is becoming logic 1, means rise time. Rise time is very high. And because of the current limiting resistor, which is RL, there will be a heat. In order to fix all these disadvantages, guys, we are entering into CMOS. Yes, this is a CMOS inverter, guys, where in place of RL resistor, we have used one PMOS. Guys, the PMOS transistors have different symbols in analog with arrow marks, in digital with bubbles. Remember, guys, whenever you have a bubble, it is a PMOS. Whenever it is NMOS, nothing, you will get it. And PMOS becomes on when its input is logic 0. And it becomes off whenever input is logic 1. That's what the behavior for PMOS. Whereas for NMOS, it becomes on for logic 1. It becomes off for logic 0. Yes, guys. And why it is called complementary metal oxide semiconductor family? Because it contains two alternate complementary transistors. One is PMOS, one is NMOS. Hence, it is called CMOS inverter. Now, guys, always remember the PMOS is always pull-up network. Means you have to connect the PMOS at the upper stage only, at the top side only. Hence, you can call this one as pull-up network. Similarly, NMOS is always connected to pull-down only. Hence, the NMOS circuit is also called as pull-down network. Now, let us see the operation. Team, here, whenever V input is 0, this NMOS becomes off and this PMOS becomes on. As it is on, there will be a current flow through R on and the CL. Yes. So now the capacitor is charging. As the capacitor is charging, guys, here the output is going to logic 1. But now the interesting point is there any rail to rail connection? No, because NMOS is off. Similarly, you take V in is logic 1. Here also, whatever the capacity is charged in previous case might be, it's going to be discharged through R on N. What about PMOS? This is off. In this case, is there any connection between rail to rail? No. Hence, guys, I conclude in CMOS, either in case 1 or case 2, there is no rail to rail connection. That means whenever inputs are stable, there is no current in the circuit. So that there is no static power dissipation in CMOS. Because in like when inputs are stable, in both the cases, current is 0 only. Now, guys, whenever inputs are dynamic, you can ask me, sir, during the transition 0 to 1 or 1 to 0. In such case, yes, there is some power dissipation in the circuit in CMOS as well. That is dynamic power dissipation. Guys, Yeah, you can ask me, sir, in CMOS also dynamic power dissipation is there. Now what to do? Just hold on. Wait for a second. Guys, whenever you are using your mobile, now the charging is going to be reduced. You don't blame the mobile company. Array, I'm using the mobile, but the charging is getting decreasing like that. You don't ask most of the times. Whereas you take another aspect. You have not at all used the mobile for 2 hours or 3 hours. Then also the charging is reduced. Then you will question to the mobile company. Array, that Bakwas company is not at all providing battery backup like that. So if the dynamic power is there, means during working, right? Then it's okay. But whenever I have not switched on my mobile, but still it is going to be a reduction in the power, like that charging and all, then people may question you. So in a design, the static power dissipation must not be present, whereas the dynamic power dissipation might present. I'll agree. If the dynamic power dissipation is less, that's fine, well and good. But there will be power dissipation when the inputs are switching. That we have to accept it. Okay. And one more aspect, team. You can see here during the charging time constant. What is the charging time constant equation? That is R on P into CL. Whereas discharging time constant is R on, like let's see, tau D, R on N into CL, because you can see here, right? So here it is there. So the discharging time constant in NMOS inverter and in CMOS inverter same only. So the discharging time constant is same. But whereas in charging time constant, the charging time constant in NMOS inverter is RLCL, but whereas here it is R on P CL, whereas R on P is very less. Okay, hence the charging time constant is less in the CMOS logic. Okay, that's what like whatever, if you speak like the disadvantages, can be overcome because no current flow through the rail to rail connection, as there is no connection. Similarly, the noise margin is also good, guys, because there is no rail to rail connection. If you ask me VOH, it is VS only. If you ask me VOL, it is 0 only, because there is no current. How can you apply voltage division principle? R on by R on plus RS into RL into VS. So in CMOS, it is VS and 0 only. That's why the noise margin problem is also resolved in CMOS. Similarly, rise time. Rise time is also smaller. Yes, guys. Similarly, there is no load resistor at all. It is replaced by PMOS. Hence, this problem is also resolved, guys. And we want to know about power aspect. Okay. That we will see in the next session, guys. I have some work, and I need to go over there. So I'm sorry. And just a second.
Yeah, sure. Yeah, we can continue in the next class, no problem.
Okay, Rajat. Thank you.
Yeah.
Yes, team. This is the conclusion. So in this class, we have discussed about SR model, power aspects of NMOS inverter, and how we fixed those like shortcomings in CMOS. Now, in next class, we will discuss about the power aspects of CMOS inverter. And then, guys, we will go to timing arcs. Okay?
Okay,
Yeah, any questions in a quick way?
okay then. Thank you,
Sir,
guys. Yeah, tell me.
Okay, right.
Yeah, you can ask.
sir,
Uh, Yeah.
In NMOS, you said na ki we can, while explaining NMOS, you said we can connect infinite number of inputs because
Oh,
it's noise margin.
no, no, no. Are you speaking regarding the NAND gate or NOR gate, or you tell me, like, can you explain, like, can you expand your question more clearly?
Sir, in one slide you have written ki
Hmm.
we can connect infinite number of inputs because its noise margin is very high.
Okay, let me go to that slide. Is this you are
Ye-
speaking, right?
Yes, sir.
Yeah,
In not.
yeah, continue.
So, sir, can you explain how means how in NOR gate we can connect maximum number of inputs?
No, 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 no.
Because
Like, no, no, no. Here, what's my point is, you can connect maximum number of inputs. If you connect maximum number of inputs, you see here, this is a NOR gate. It's a two input, A, B, so that in this numerator, I got R on by 2. See, ideally, I'm expecting VOL to be 0. Then only my noise margin will be very high. I'm expecting VOL is 0. But in this NOR gate, if you take NAND gate as well, this VOL is somewhat high.
right.
Whereas in this NOR gate, this R on by 2, as it is less, this VOL becomes less.
Yes,
Now,
yes,
to
understood,
be
sir.
frank, understood?
Yes.
Yeah, yeah, good. That's what. Good.
Oh,
If you ask the questions, we will be happy that you are following the classes and all.
Yeah. Okay, then thank you guys. Thank you so much.
Okay, then. Okay.
Thank you
Have
so
a nice, happy weekend, team. Bye, Rajat. Bye, team.
much.
thank you, sir.